Hello physics students. Today we're going to be learning about the power in a resistor or any electrical circuit. To illustrate the concept, I have a demonstration set up here for you. Now what I have here, which you probably can't even hardly see, is a very thin wire connected between these two alligator clips which are connected to this power supply. Now the wire, I'm going to come closer and show you, is, as I said, extremely thin. So you see it next to my fingers here. It looks like basically almost like a hair. And it may look like bare copper wire, but it actually isn't. It's coated with something that acts like a resistor. Now normally we cover wires with plastic or rubber or something like that. This is sort of some kind of painted on material because the wire is so thin, they wanted to keep the insulation very thin. So what I had to do first when I set this demonstration up is I had to scrape the wire clean at the very end of that insulation on both ends so that the alligator clips would successfully make a connection. So right here, this is cleaned off wire at the alligator clips. What I'm going to do is, without any resistance in the circuit, I am going to turn this on and pass electricity through this. What you're going to see is that this wire heats up, and the way we're going to see the evidence of that is that it'll first begin smoking as that insulation burns off. So there it is. You could hopefully see that smoke. And now the insulation's burned off and the wire's glowing orange. We're basically at an equilibrium where the heat is radiating out as quickly as the power supply is putting it in. And when we're talking about rate of heat going in or out, really what we're talking about is the joules per second. In other words, the power. So we're at this equilibrium, but if I crank this voltage higher, it'll pass more current through that wire, so the electrons going through the wire will slam into the atoms even more rapidly, producing more heat so fast that the wire will not be able to dissipate it fast enough. And then we're going to see something pretty dramatic happen. The wire actually melted. I melted metal with the electric current passing through. So that is a demonstration of power going in extremely rapidly, heating up the copper wires. Now, if I could keep the heat coming out as quickly as I was putting it in, the wire would not melt. And one substance that's very good at absorbing heat and pulling it away from wires is water. So this is another demonstration I'm going to set up here. I got a little small beaker of water, and I'm going to place a big coil of that wire that I just melted coiled up into the water, so that when I pass the current through it, the water will be removing the heat out of the copper pretty effectively. And then we're going to basically see that we could heat up the water through the electrical power. So let me submerge this and make sure everything's underwater so that the heat's effectively. Now what I'm going to do is turn this up, and let's see. Yeah, that looks good. Maybe 2.5 amps is what so I'm passing a certain amount of current through here, but it'll take a while for this water to heat up. So let's move on with the notes, and when we reach a sufficient temperature, I'll come back to this in a minute or so. Okay, so let's begin with the notes for the day. The topic for today, power in a resistor. Now, before we begin with the analysis, I want to just call your attention to the fact that often in problems or on questions, they don't directly say the word power. They'll ask for you to calculate the power, but they'll use a phrasing where they say the rate at which energy is consumed, or calculate the rate at which heat is dissipated in a resistor or into the water, or something like that. And so when you see the word rate, of energy. What we're talking about is power, because power is work over time, so it's a rate of energy. So just a reminder, or just pointing that out so that you don't get tripped up. When you see the word rate, they're probably going to be asking you for the power. So here's a basic circuit. Voltage source, a switch that when it flips down, it makes a connection, passing current through the resistor. And rather than just writing down the formula for calculating the power, what I'm going to do is derive it today, because that's part of the curriculum. It says that you have to actually be able to make this derivation. So the first place we begin is to realize that the energy, or the joules, is equal to the charge times the voltage that passes through a circuit. Remember, voltage was joules per coulomb, so if you move the coulombs to this side, that's the basic expression for the energy delivered into a resistor or into a certain water, whatever the circuit is delivering energy to. So now we combine that with the fact that power is the work over time, so replacing the W with QV, then we could say QV over T is equal to the power. Now, if we just combine these or lump these Q over T together, we see that that's the current, the coulombs per second. So here's the expression for the power in an electric circuit. It's the current times the voltage. So that's one expression, but there are other forms of this. If, for example, I replace I by, oops, not V squared, but I by V over R, that's just Ohm's law. Then I can get rid of current here, and then in addition to IV, I have V over R times V, or V squared over R. Or if I get rid of V with IR, that's also Ohm's law, just V equals IR rearranged, so I have I times IR, or I squared R. So these are three forms. Obviously, the formula you're going to use is the one that's most convenient for the data given. If you're given the voltage and resistance, you're obviously going to use this for the power. And then a reminder that the energy, therefore, is power times time. So once you have the power, the wattage, which all of these deliver, generate watts in a circuit, then you're just going to multiply by the seconds. Watts times seconds is joules. Now, this is just a little aside, but in the case of your home, when you're buying electricity from the utility company, they sell you, in a sense, joules, but they don't charge you for joules. What they charge you for is power times time, but in units that are more convenient for an electric bill, they charge you in kilowatt hours. So because a typical house uses so much energy, to charge you for joules would make your electric bill look, pretty alarming. Oh, I consumed this many millions of joules. Oh man, I'm spending a lot of money, or maybe even billions of joules. So they sell energy in kilowatt hours, but it's still a unit of energy. All right, so that's pretty much it for the notes, because we're just going to be, in the homework, applying this formula, these set of formulas to calculate various things, just plugging data in. So, but I do want to also show you a few things that deal more with the practical aspects of this formula. So the first thing I want to mention, before I do, looks like our water is boiling. So just a few minutes, and hopefully you can see that the water is boiling because of the power being delivered to it, the electrical power. Instead of the wires melting, they're heating the water up and boiling it. So that's basically one application of this with heating elements. I did turn up the current a little bit to 5 amps to get it to boil a little bit quicker. So interesting demonstration. Now, how does this relate to everyday circuits and electricity in your life? Some interesting stuff, so I just want to sort of talk about that for a while. It doesn't, I never created a pause to allow you to copy this down. Hopefully you did already, but if you haven't, then at least you could write that down. So I'll create a pause. Okay, so how does this relate to electricity transmission in everyday life? So let's suppose you have some source of electricity here. And of course, with wires, we deliver it to some load over here. So this is basically like possibly a house or an appliance. Now, at the source, there's a certain voltage, and we hope that that voltage gets to the house to run appliances, okay? So, but the problem is, if there's current in these wires, then there's also voltage in the wires from IR. And no matter what you do, you cannot eliminate the resistance out of the wires because, as we learned, any conductor has a certain resistivity, a certain length, certain area. It'll have a certain resistance, and then when current passes through, there'll be a certain voltage that's produced just in the wire alone. And so the power at the source is equal to the current times the voltage at the source. And the power where you consume it will be equal to that same current times the voltage that's delivered. But since this is less than the voltage at the source, the power at the source is greater than the power at the house. So basically, what that means is this can create some problems. For one, when it comes to the utility company, the problem is that they're generating a certain amount of electricity, producing a certain amount of energy, buying a certain amount of energy. When they buy coal or they buy natural gas, money to produce this energy. And they're having to produce more energy than we're getting at the house. And we pay for what we get at the house. So they're losing money because of the wires. So it's a money issue. And we'll talk about that in a minute, how they try and minimize that. But this can even cause problems in your own house. Let's suppose this source is your circuit panel, and this is like a tool you're running in your garage. So if the current is very small, there isn't much voltage loss in the wire. So if this is 120 volts at your panel, you're getting pretty much 120 volts at the appliance that's using the electricity. But for a tool, like maybe an electric leaf blower, or if you're using a saw outside with a long extension cord, that draws quite a bit of current out of the source, out of the electrical panel. And then what happens is, because with more current in the same wires, you're going to get more voltage loss, and this can drop significantly. And so the problem with that is if the tool doesn't get enough voltage, it could be running too slowly for it to cool itself with the fan blades in the electric motor, and it could overheat. And so too little voltage can result in the failure of electric motors. So that's a real problem when you have long extension cords that have significant resistance and a significant amount of current, you're going to get a significant voltage loss, which can harm appliances or make them not function as they're supposed to. This is why when you use tools that use a lot of electricity, you at least try and minimize the resistance by getting as thick a wire as possible to minimize that resistance and sort of prevent damage to the tool. But here's the problem. We talked about this when I showed you the videos of the electric utility workers working on those high voltage power lines. And the problem there is that very often for the utility company, the power plant is thousands of miles away from the people using the electricity. With thousands of miles of length of wire, you're going to have quite a bit of resistance and then quite a bit of voltage loss or heat loss in the wires. Like when I melted this little wire, well, that was an extreme case of heat loss in the wire. But even if you don't melt the wires, they're going to be heated up and radiating energy out into the air. So how do they minimize that loss and save themselves some money? Well, a reminder that the voltage that they operate those lines at is extremely high. So I have another video clip to remind you of what we saw when we were studying, and I showed you that video of the people working on the power lines on YouTube. All right. Guess I won't zoom in, keep it a little easier. So now we won't really see much of the sound, but this is, hear much of the sound, but you could see these are not just the small telephone poles. This is where you see those giant telephone poles that lift the power lines much higher than the trees. And you remember, they come in with a helicopter, they touch the wire, and remember I said this is, well, here it says 765,000 volts. The voltage is so high that they have to keep these lines so high because the sparks would hit trees and set them on fire. So these are power lines. These wires right here have that high voltage and they have enough current and voltage to power cities or counties. So again, this is that high voltage power line. Now what I'm going to do is stop the video and explain more the physics, the power analysis of why they lift that voltage so high. All right, so I didn't create a pause yet, so let me just lower this a little bit. So if you need some time to catch up, go ahead and copy this down. Okay, so let me try and draw this as best as I can here. So minimizing maybe a little bit lower. So this is the generator. These power lines are thousands of miles long. And then here we have something called a transformer. So this we're going to see is a relatively small current here. And there's a delta V here, 1, that comes into the transformer from this power plant, this generator. After going thousands of miles, that voltage is still hundreds of thousands of volts. Send that into a house, sparks will be shooting out of the outlets, electrocuting people, houses will catch on fire. It would be a disaster. So what we need is a transformer to change the voltage and also in the process change the current. Now, the transformer, later in the year, we're going to learn how the transformer, the physics behind how it converts one voltage to another. Something to do with how many coils, electrical coils are in there, but we don't know the physics behind that yet. But just what we need to, all we need to know is that it changes the voltage, but in the process, it basically, the power going into the transformer is more or less the power going out. There's some losses in every sort of electrical device, but let's just assume there are no losses. It's a perfect transformer. What's happening on this side is we have, over that thousands of miles, a relatively small current. Why? Because we cannot change the resistance in the wires because they're thousands of miles long. Okay, maybe we could thicken them, but if you make them too thick, they're going to be too heavy, they're going to break. Also, it's going to waste a lot of money. So the thousands of miles, that's the real problem which creates significant resistance. To minimize the losses, what you want to do is you want to make as little current as possible, because power in the wires, one expression is I squared R. Again, you can't change this, but making as small a current makes as little power loss in the wires. So on this side, we have a relatively small current, but an enormous voltage, 760,000 volts. And then what comes out of the transformer is it lessens the voltage. So now I'm going to write delta V2, small compared to this. But in the process, because power in has to equal power out, if you lessen the voltage, what happens is the current coming out here is much larger, goes into the homes, and now the voltage is safe. So that's the kind of physics of why they made the voltage so high, to minimize the power losses. But then you need this. Without this, it would go into houses and set them on fire. So you need the transformer to make the voltage go down, and then you get more current as a result going into the homes. So that's the reason why they had the voltage that high. All right, so that's it for today. Just a reminder that the things that you need for the homework and the AP, the calculus, are the formulas that I wrote out on the board. P equals IV, P equals V squared over R, P equals I squared R. That gives you the power in any electrical circuit, a resistor or an electric motor. All those expressions give you the power in watts, the joules per second. And then you could use that to get the total energy by multiplying by seconds, time. Power times time equals the energy. So that's the information for today. I hope you enjoyed the information and the demonstrations. I'll see you in the next physics video.